Hi, I'm Ben, and today we're graphing trigonometric functions. Our objectives today: transformations of trigonometric graphs, graphing trigonometric functions by hand, and then simple harmonic motion. So let's first talk about how the graph f of x is equal to -2 sine of x minus pi over 2 can be obtained from the graph of the sine function f of x is equal to sine x. Well, take a look first at the graph of sine x. You can see that it crosses through the origin, moving up and to the right, and it oscillates between -1 and 1. So f of x is equal to -2 sine of x minus pi over 2. This part here, minus pi over 2, is a phase shift. It shifts the entire function to the right, pi over 2. The -2 sign here, the negative will cause it to reflect over the x-axis. So instead of moving up and to the right through the origin, it'll move down to the left from the origin. And the 2 is going to amplify it. So now instead of oscillating from -1 to +1, it'll oscillate from -2 to +2. So here you can see the graph of both, the sine curve and the new curve. You can see that the new one goes from +2 to -2, and it's shifted and it's upside down. So that's how we get from f of x is equal to sine of x to f of x is equal to -2 sine of x minus pi over 2. Let's talk about amplitude, period, phase shift, and vertical shift in general. The amplitude, period, phase shift, and vertical shift for the graphs of y is equal to a sine b sine of the whole group b times quantity x minus c, closed group and quantity, plus d, and y is equal to a cosine of the quantity b times the group x minus c, closed group and quantity, plus d, with b greater than 0, may be determined as follows. Look at this graph here. The amplitude is the absolute value of a. That's how far it is from the line that crosses through the middle of this whole thing to the very top or the very bottom. The period is 2 pi over b. That's how long it takes to get from the crest to the crest, or the trough to the trough, or from the midpoint going down to the next midpoint going down. That's the period. The phase shift, c, is how far we've scooted it to the right, and the vertical shift, d, is how far we've moved it up. So phase shift is equal to c, vertical shift is equal to d. A vertical shift of d units upwards occurs when d is greater than 0, an absolute value of d units downward when d is less than 0. So if d is 2, we move the whole thing up 2, and if d is -2, we move the whole thing down 2. So let's look at a specific equation. For the graph of the equation y is equal to 2/3 sine of the group 6x plus 3 pi minus 5/2, identify the amplitude, period, phase shift, and vertical shift. And you don't have to graph this equation. So let's first rewrite this. Instead of y is equal to 2/3 sine of this whole weird thing here, let's rewrite it into a form we know how to handle. Call that the sine of 6 times the group x plus 1/2 pi minus 5/2. That should make this all a lot easier for us. First off, the amplitude. Well, the amplitude is just simply the coefficient out here in front of sine, 2/3. The period, that's 2 pi over 6. Remember, it's 2 pi over whatever we have out here. 2 pi over 6, that's just pi over 3. The phase shift, that's equal to pi over 2. Remember, we're shifting it here 1/2 pi or pi over 2, and we're moving this to the left because it's plus. And then lastly, the vertical shift. That's equal to -5/2, or 5/2 downward. Let's take a look at another function. F of t is equal to the cosine of pi t plus 2. So find the amplitude, period, and phase shift of this, and then sketch the graph of f by hand on the interval -2 pi to 2 pi. Well, first off, the amplitude is simply 1. This is just the coefficient of 1 out there. The amplitude is equal to 1. We can think of this as the period. That's 2 pi over pi. Remember, you can think of this here as cosine of pi times t, like that. So here's the coefficient out here, so 2 pi over that. The period's simply going to be 2 then. And there's no phase shift because we're not adding anything to the group here, so there's no addition or subtraction. There's no phase shift. And the vertical shift, that's equal to 2 upwards. So if we want to graph this by hand, this is a cosine function. We're going to have the new center of this line, the new line that goes through, will be at 2 because we've shifted the whole thing up 2. We know that it has an amplitude of 1, and because it's a cosine function, it's going to go through the y-axis here 1 unit above the midpoint. And it's going to have this shape. Now, how far out does it go? We're graphing this on the interval -2 pi to 2 pi out here, and 2 pi is roughly 6.28, and each of this here, from here to here, is 2. So here's 2, 4, 6, 2, 4, 6, so right about there. So here's one for you to try. Find the amplitude, period, and phase shift of f of x is equal to sine of 1/2 x. Once you do that, sketch the graph of f by hand on the interval -2 pi to 2 pi. So let's see how you did. Well, first off, let's write this as sine of 1/2 of x, like this. So first, find the amplitude. Well, that's pretty simple. There's just a 1 out here, so the amplitude is equal to 1. The period is equal to 2 pi over 1/2, or 4 pi. And then there's no phase shift because we're not adding anything in here, and there's no vertical shift because there's nothing out here to the right. So we need to graph this by hand from -2 pi to 2 pi. Now this is a sine function. Its amplitude is 1, so it's going to go from 1 to -1. And because it's a sine function, it will cross the origin on its way up and to the right. So remember, the period here is 4 pi, so it's going to take from here to here to get through a full period. So that means it's going to do something like this. Come down to 1, up through the origin, up to 1, and then down to 2 pi. And it'll look something like this. Now let's try an application problem using this idea. A particle undergoing small oscillations about a point of stable equilibrium executes simple harmonic motion. An example might be a small weight on a spring that bounces up and down when displaced from its natural length. When an object undergoes simple harmonic motion, its distance or its displacement from its stable or natural place can be modeled by either S of t is equal to a sine of bt or S of t is equal to a cosine of bt. So let's try an example problem like this. Consider the spring and weight shown here. Here's the weight. It naturally rests at S equals 0. But sometimes you pull it down to S equals -2, and sometimes you pull it up to S equals 2, and then you let it go, and it bounces back and forth between 2 and -2. So when the spring is stretched and let go, it'll oscillate up and down. If the displacement S is plotted after t seconds, a sinusoidal graph will result as shown. So at t equals 0, you had it pulled down to -2, you let it go, it went up to 2, back down to -2, and so on all the way out here. So this is what the graph looks like. The number of oscillations per unit time is the frequency. The frequency f equals the reciprocal of the period p. That is, f is equal to 1 over p. Since p is equal to 2 pi over b, it follows that f is equal to b over 2 pi, or equivalently, b is equal to 2 pi f. So our formulas for s of t can be written as s of t is equal to a sine of 2 pi ft, or a cosine of 2 pi ft. So for a specific example, suppose that the weight on the spring has an initial position of s at s of 0 equals 2 inches in a period of 0.5 seconds. So A, find a function s given by s of t equals a cosine 2 pi ft that models the displacement of the weight, and B, evaluate s of 1. Is the weight moving up, down, or neither when t is equal to 1? To do this, start with A. The f, the frequency, is equal to 1 over p, and that's equal to 1 over 5. Remember, we're given that the period is equal to 0.5 seconds, or half a second, so 1 over 0.5 is equal to 2. So s of t is equal to 2 cosine 2 pi 2t, or that's equal to 2 cosine of 4 pi t. So for B, we need to evaluate this when t is equal to 1. So s of 1 is equal to 2 cosine 4 pi times 1, and that's equal to 2 cosine 4 pi. Well, cosine of 4 pi is simply 1, so 2 times 1 is 2. And it's neither moving up or down at that point, because it's just hanging out there at the top. Today, we worked on trigonometric functions. There are a lot of problems like these in your book, and they need some work. So give it your best try and come back next time, and we'll do a new lesson.